Alright, welcome back to the last lesson for this week where we're going to be looking at Le Chatelier's principles. So this whole thing is, there's no calculations based on this, it's mostly just realizing what's going to happen to a system at equilibrium if we disturb it or stress it or change something. So what Le Chatelier's principle states, when a chemical system is at equilibrium, is disturbed by a change or stress, the system will react in the direction that opposes the stress. So we're going to be looking at three main ones that will actually change equilibrium and look at ones that won't actually affect it at all. So what a new equilibrium means is that the reaction will either favor the forward reaction, so forming more products, or it's going to favor the reverse reaction, forming more reactants. It does not mean that the equilibrium constant will change, only temperature will actually change this. So let's look at some of the stresses and of course how things will change. So the first stress that we can pose on a system at equilibrium is a change in concentration. So this is by either adding or subtracting one of the reactants or the products. So if the concentration of one or more reactants is increased, the system will oppose the change by converting more of the reactants into products. So another way to think about it, if we increase the concentration of a product or a reactant, it's going to favor the opposite direction, meaning that it's just going to go and favor the other way. Whereas if we decrease the concentration of products or reactants, it's going to favor the same side. And another way to think about it, if we take away one of the reactants, the equilibrium will shift to try to produce what is essentially being lost. And of course, changes in concentration will have no effect on the value of the equilibrium constant. So that means that if you do evaluate the equilibrium constant, that number will stay the same. However, the concentrations at equilibrium can change. Now, the other type of stress that can happen is a temperature change. Now, this is the only one that will affect the equilibrium constant. But for this right here, you have to think about energy is treated like either a reactant or a product. So that means for an endothermic reaction, energy is on the reactant side, so we're going to treat it exactly how we did with these up here, right? So an increase is going to favor the opposite, and a decrease will favor the same side. Now, an exothermic reaction, the energy is on the the product side. So another way to think about it, if a system is cooled, right, or we decrease the temperature, the equilibrium shifts so that more heat is produced favoring the same side. And that's the exact same thing that we have up here, is a decrease in concentration favors the same side. Well, if we decrease the temperature, it's going to favor the same side. If we increase the temperature or heat it, it's going to shift away from the heat, or the opposite side, which is the exact same thing as above. Now, change in temperature is the only stress that can change the value for the equilibrium constant. And finally, or this is what you see here, so if the equilibrium constant increase, shift towards the product side, and of course if the equilibrium constant decreases, it's a shift towards the reactant side. Now finally, the last change that we can get is a change in volume or pressure. So change in volume and pressure are going to be the same, because if you remember from Boyle's law from Chem 20, if you increase volume and pressure are inversely proportional, meaning that when you increase one, the other one decreases, right? So when you make the volume of the container smaller, pressure increases and so on. So that's what we have right here. Volume and pressure are inversely related. That means if one goes down, so if volume goes down, pressure goes up, or if volume goes up, pressure goes down. Now, concentration is also inversely related to volume as well. So that means as the volume gets bigger, concentration gets smaller. As volume gets smaller, concentration gets bigger. So what this means is that a decrease in volume causes an increase in concentration, and therefore will shift towards the side that has fewer moles of gas. So what this means is, we're going to get in one of those examples later, but you need to look at your balanced chemical reaction and count the total number of moles on each side of the reaction. So how many molecules are on the product side, how many are on the reactant side. So if we increase the concentration, it's going to shift to the side that occupies less space or has fewer moles. Now, if the number of moles of gas are the same on both sides of the reaction, then any change in volume will have no effect. And also, if you read a question where it says addition of an inert gas like helium or argon is not going to have any effect on equilibrium at all. Because if it's an inert gas, we're just adding another gas. We're not changing the volume, we're not changing the pressure, and we're not changing the concentration. And of course, finally, catalysts, they do nothing. All they do is just decrease the time required to reach equilibrium position, but does not affect the final position of equilibrium or the equilibrium constant. So right here is we have basically just a summary of the stress, the shift, and a little brief explanation of why. So it'll be very handy to kind of pause the video and read through these here if you must. But we're just going to go right into looking at some examples. Now, a lot of these questions were going to come with color change, because if we're looking at equilibrium systems that have color, we can predict what color we will see once a new equilibrium is established. So for example, we have right here, we have all aqueous ions. So this is an equilibrium for the chromate ion turning into the dichromate ion. So chromate ion is yellow, dichromate is orange. So depending on which way the equilibrium shift, for example, if we shift towards the reactant side, we're going to see more chromate. So if we produce more chromate, we're going to see more yellow. Whereas if we shift towards the product side, therefore, if we use up our yellow chromate and produce more orange dichromate, the overall color we're going to see is more orange. So that's how we're going to predict the color change based on which way the equilibrium is going. So we have different scenarios here, A, B, C, and D, and E, where we're doing a stress, and we have to figure out what is the stress. So it's either going to be a change in concentration, a change in temperature, or a change in pressure or volume, and we're going to figure out which way the equilibrium is shifting. So for the first one, if we add a crystal of sodium chromate, right? So we're adding, now remember this is an ionic compound, it's going to dissociate into sodium ions, and specifically the chromate ion. So what we're doing is increasing the concentration of CrO4 minus in this example. Now, from Le Chatelier's principles, back to the first one, it says that if we increase the concentration on one of the reactants, the equilibrium will shift in the opposite direction. So that means if we're increasing chromate here, it's going to shift in the opposite direction. So we're going to get a shift to the right, or we're going to form more products, which we will see orange, or products are favored. So that is how we can break apart the stress, the shift, and of course the orange or the color that we will see. So we're going to go through these here with kind of all these here. Now you can pause the video and try them on your own as well, or we can just kind of go through. So the next one be a crystal of sodium or potassium dichromate is being added. So we're still adding, in this case right here, we're adding the dichromate ion. So very similar, if we're adding this, so the concentration of the dichromate is going up. When we're increasing or adding, that means the equilibrium shift in the opposite direction. So we're increasing Cr2O7 minus. That means we're going to shift in the opposite direction. And we should see more yellow, because reactants are favored. Now I'm going to leave out the reactants or products being favored because showing the direction of the shift will say the same thing. So the next one we get a few drops of concentrated acid is added. So in this case right here we're increasing the concentration of H3O+. So whenever we increase the concentration of something, the equilibrium shift in the opposite direction. So it's going to shift right, and we should see more orange being produced. Now the next one, this is one of the ones where it's first time something is being removed. So in this case right here, how we're going to note this one, we're going to decrease the concentration of water. Right, so we have water right here, so we're going to decrease the concentration. Now, when we go back, or if you look back to the previous page where it says stuff about concentration, it says when you decrease the concentration of something, it's going to favor the same side. So that means equilibrium is going to shift to try to produce the water that it's losing. So that means we're going to shift to the same size of water, so that's going to shift towards the formation of the products, which we're going to see more orange. And finally, the last one. So we have a few crystals of NaOH being added. So this one, if you remember sodium hydroxide, this is a base, right? So what happens when we get acid plus base coming together? If you remember, this is a neutralization reaction. So essentially what we're doing is we're decreasing the concentration of H3O plus by adding a base. So it's going to shift to the same side, and we're going to see more yellow. So that's kind of how we break up the Chatelier's principles, and these here, of course, are all aqueous. We never seen any temperature or anything like that because there was no energy unit here. But remember, temperature is just like the reactants and the products, is that if we add energy, it's going to shift away from equilibrium or shift away from the energy unit. If we decrease it, it's going to shift towards. And that's where we get into our second one. Now this right here, where these are all gases, so this is where volume and pressure may actually take into account. So first thing, I do kind of want to rewrite this as well, but also bring in the whole idea about number of moles of gas and how that might change it, because if you look back on here, when we had change in volume, right? So if we increase the concentration, it's going to shift to the side with fewer moles of gas. Well, this one's going to come up here, where when we count the total number of moles of gas on each side, with 2 SO3, there's only 2, oh, sorry, that's a 3. There's only 2 moles of gas on our reactant side in total, whereas on our product side, we have 2 moles of SO2 plus 1 mole of O2. There's 3 moles of gas on this side, so we have an unequal number of moles, so our reactant side has fewer moles than our product side. So if we change the volume, we'll have to see which way that goes. And then finally, if we want to cross out our energy unit, as we know this is positive, so this is endothermic, that means that the energy unit is on this side. So let's look at all these here. So sulfur dioxide is added to the system. Now these here, we've done these like above here, so we know when we're adding something, it's going to shift away. Sulfur dioxide is right here, so it is one of the products. So if we increase the concentration of SO2, the shift is going to be back towards the formation of our products, and we should see brown color being produced from the sulfur trioxide. Now sulfur trioxide is removed, so we decrease the concentration of SO3. It's going to shift to the same side. So that means shift towards the reactants. And same thing, we should see more of a brown color being produced. Now C, D, and E are 3 new ones that we haven't seen in our previous example. That's why I kind of went over A and B really quickly there. So in this one here, the volume of the reaction container is increased. So this is where you had to remember, if we get an increase of volume, this is the same thing as saying a decrease in concentration of everything. So it's going to shift to the side more moles of gas. So the reason we know it's going to shift to the side of more moles of gas, on this one right here, it said a decrease in volume causes an increase in concentration, so it's going to shift to the side with fewer moles. Well, if we do the opposite, so if we increase the volume, decrease the concentration, it's going to shift to the side with more. So that's what we have right here, I believe. Volume reaction here is increased, so we decrease concentration, so it's going to shift to the side with more moles, which that is our 3 moles of gas up here, right? So it is going to increase the concentration. So we should see the colorless color being produced. Now, For D, it says reaction container is placed in an ice bath. Well, this is cooling it down. This is actually decreasing the temperature. So remember, when we decrease something, it shifts to the same side. And by placing the energy unit as a reactant, because it's endothermic reaction, that means it's going to shift left, and we should see the brown color again. Finally, a catalyst is added to the system. Remember, catalysts do nothing, so no change whatsoever. So definitely the C and D are new ones, but that is perfectly okay because in our workbook there's going to be a lot of different examples and stuff like that. Now the last example before we get into the old diploma questions is that looking at graphical analysis of the Chatelier's principles and just showing you what they actually mean. So you have our graph right here. We have concentration and time. We have different stresses at A, B, C, and D. So we're just trying to figure out what they actually mean. Now, also for manipulation, we can tell that energy unit's here, so it's exothermic, and if we want to count the number of moles on both sides, it's kind of handy to do as well. We got 1 mole of nitrogen plus 3 moles of hydrogen, so we got 4 moles on our reactant and only 2 moles on our product. So now if we know if we're changing volume, the shift will determine which side has fewer moles. So at stress A, we will notice that at point A, we can tell NH3, so more NH3 is being produced, more N2 is being produced, new equilibrium is being established. But we see this point right here. This tells us that only the concentration of H2 is increasing. Now that is why the stress, we have an increase in H2, so we get a shift. Because it's increasing, it's going to shift to the opposite side. So that's why a shift increase in H2 here is going to shift over here. So this is why we see the concentration of ammonia starting to go up here and equal out, and the concentration of nitrogen going down. It's because the nitrogen is getting used up, but more ammonia is being produced because of that shift to the right-hand side. So you get a shift right. Now at point B, we'll notice nothing. There's no change. We can tell that there's no stress. So at point B, this is what a catalyst is added because really there's no new stress. Nothing has changed. That's why on the previous page it said when a catalyst acid added, no change whatsoever. Now at point C, notice how we have the concentration of hydrogen goes up, concentration of nitrogen goes up, concentration of ammonia goes up. So we have all 3 changing in concentration. So when this happens, there is a change in volume. In this case, well, if all the concentrations are going up, that means we have a decrease in volume. So that's what we have right here at point C. We got a decrease in volume. Now with this right here, when we get a decrease in volume, we get an increase in concentration. So that means it's going to shift to the side with fewer moles of gas. And that is because there's less space. So it's going to shift to the side that has fewer moles of gas, which is the ammonia. So that's why we can see the concentration of ammonia after this stress. The ammonia goes up and our 2 reactants go down a little bit before a new equilibrium is reached. All right, and finally our last one. So you can tell that there's no sharp increase or decrease in concentration in anything. It's just a new equilibrium is being established. This is a change. This is the only stress that we haven't really looked at yet. We have a change in concentration, looks like this. Only one of them will be affected. A change in volume, all of them will be affected. And finally, a change in temperature, just a new equilibrium is being established. In here we can tell the concentration of ammonia is going down, so that means the shift is going back the other way. And because energy is a product over here, the only way to get the shift to go in the opposite direction of our energy unit is we need to add energy to get it to shift away. So at point D, we get an increase in temperature because the shift is going back towards the formation of our reactants. And that is how a graphical analysis of the Chatelier's principles will look. So you will need to know how each one of these here look. Because if you are given a graph, you'll need to know kind of which one is occurring. Now, just kind of jump ahead a little bit. Spoiler, boom, we see graphs. But that's not a Chatelier's principles question. Sorry. But they might show up later. So, we do have a bunch of diploma example questions on the Chatelier's principles. The best is to just kind of pause the video right now and try them, and just to see if you can get them. And I'm just going to put up the answers here now. So for the first one, we have which of the following observations is not an indication that a system reached constant equilibrium, or reach equilibrium, that is a constant mass. Because for equilibrium, pressure, temperature, and constant number of gaseous molecules are all there. Mass we haven't dealt with at all. For 12, when applied to the equilibrium above, stresses that will cause a shift towards the reactants are numbered. So of course we're still talking about this one right here. So a shift towards reactants is this way, right? So our energy unit here, but anyway, you have to go through. So if we add H2, this is definitely 1, because if we add H2, it shifts in the opposite direction. Add CO2? Nope, because if we add CO2 here, the shift is going to be towards the products. So it is definitely not that one. Add a catalyst will do nothing anyway. Remove CO? Nope, because that is going to shift in the... They'll shift to favor the same side as where CO, so they'll shift it back that way, which that is also a negatory. Remove CH4? Yes. And decrease the volume of the reaction container. This one right here, well, we have 2 moles, 4 moles. So if we decrease the volume, we increase concentration, and it's always going to shift to the side with fewer moles, less space to move around. So yes. Last one is 6 as well. So we got 1, 5, and 6. Our next one said, which of the following sketches best represents the progress of the system at equilibrium? Now this one here is definitely a little more challenging, but the big giveaway that we're looking at is this right here. So we see the equilibrium constant is 3.3 times 10 to the power of 10. Now this is products greatly favored. Because remember, equilibrium constant just above 1 favors the products, but now this is way, way, way above 1. So we're looking at the products massively being favored. So our reaction, a technician puts 1 mole of methane and 1 mole of CO2 in a container and seal it until equilibrium. So of course I think we're still using the reaction from our previous one there. So our products, just a little reminder of CO and H2. So if the products are greatly favored, we want to see the biggest concentration of our products and a very low concentration of our reactants, which comes about in D. Right, like this one here, we do see the concentration of the products more, but like I said, this product's greatly favored, so we should see, boom, definitely a lot of products being made there. And finally, last but not least, sorry, this isn't the last one, but another one here. So in order to calculate the equilibrium concentrations, what expression where X represents the change in concentration, so CH4 could be. So of course, as we know, for this one right here, if you look at what we had right here, you will kind of need to do a mock ice table for our reaction, and you could potentially not do the ice table, but it helps. Alright, so our ice table, our reaction was CH4 plus CO2 producing CO plus H2, NO2 and 2. So remember from the question above, said we initially place 1 mole per liter. There's 0 for these here. these here minus x plus 2x plus 2x. So our ice table looks something similar to this. Now we can tell when we do Kc is equal to CO squared H2 squared over CH4 CO2. So we end up doing that, and we'll notice the expression that best fits when we actually solve everything. We should end up getting B, because the concentration at equilibrium is 2x and 2x, and of course these are all squared. And so our best expression is B, not C. So you just want to be careful for those. Right, and of course just because that Alright, so when you plug it in, you get this, and you simplify two of these here by just going 1.00 minus x squared. So that's why we end up getting B. Alright, and our last page. So same thing if you want to just kind of pause the video and kind of go through these if you can. But either way, so we have methanol produced here, we have our reaction, we have equilibrium concentration measured as the following. So of course with this one here, all you're really doing is putting in, you're asked to evaluate for the equilibrium constant. So we write out our reaction, it looks like this. We plug in our values, and when you're done, hopefully you get C. Alright, because this goes here, this goes here, don't forget the squared, and that goes in there. And last but not least, heating the equilibrium system represented by the equation above will shift to equilibrium blank, and the value of Kc would blank. So we can tell this is negative, it's exothermic, so that means it goes here, right? It goes as a product. Now if we heat up, right, so we're adding energy, that means it's going to shift away to produce more reactants. So we know that it is producing the reactant, so we can scratch out D and C. Now as for the value of Kc, remember we have products over reactants. If we increase the reactants, the value of Kc decreases. And that, of course, is all of those. So, that is Le Chatelier's principles, and of course even some of the other ones, and that kind of concludes everything that we want to get done for this week. So please go do all of the workbook stuff and make sure to log on for the extra help session next Thursday. And next week we are going to be looking at acids and bases, so our new definitions of acids and bases, and solving equilibrium concentrations with those. So see you guys next week.